here's the set of all integers, the set of all rationals, the set of all reals, the set of all complex numbers, right? And we want to see which of these are closed under plus or times or divide, right? Well, if you take two integers and you add them together, what do you get? You get an integer. So integers are closed under addition, right? Here is a first order logic statement that you should all be great with. You take any two values, x and y, that are in our set S, which is in this case is integers, and you add them together and you get an integer, right? That means it's this set is closed under this operation. Now, if we multiply, are integers closed under multiplying? Yeah. Take two integers, you multiply them, you get an integer. Are they closed under division? No. 2 divided by 2 is an integer, 3 is an integer, but 2 divided by 3 is not an integer. It's a rational, right? So rationals are closed under division, but integers are not, right?
Sorry, could I ask
Yeah.
a question?
Yeah.
What do you mean by closed? Like,
what I mean is what we're saying up here. Can you see this expression here? For any, if you take, I'm going to say set S is closed under operation F, is if you take two objects from set S and you do the operation, you get something in, right? So here, let S be the people that are at my house. I throw a party, right? And we want, one example I give in 3101 is a wedding. If you have a wedding, you want the wedding to be closed under friends. So if I invite somebody, then I need to invite their friends, right? So anybody's in the set, you have to invite, if it's closed under the friend operation. So here, integers is closed under addition. Why? Because you give me two integers, you add them together, what do you get? You get an integer, right?
I get the concept. I just wanted to know what closed means per se. Like, does it mean that it works under this or it has to be this? Like, what does the closed like
What it
mean?
means, set S is closed under operation F, is if you take any two objects that are in S, you do the operation on them, what you get is still in S.
Okay.
That's what it means, right? So for example, the integers are not closed under division. Why? Because I can take 2 and I can take 3 and I divide them and I don't get an integer, right? But the rationals, what's a rational? A rational is a fraction. Are fractions closed under division? Yeah, you take, if x is any rational and y is any rational, and you divide, you get a rational. A rational is any number that can be expressed by integer divided by an integer. All right, what about square root? When x is positive, if you take the square root, it's closed, right? Take the square root of a positive real number and you get a real number. But if you take the square root of a negative number, you get a complex number. So the complex numbers are closed under square root. You take any complex number, you square root it, you get a complex number. All right, so what are we doing here? This is the set of all computational problems that can be solved by a DFA. You take two languages here, right? So a computational problem in ways of language. It's the set of all languages that have DFAs that can solve them, right? So here, take one language that can be solved by a DFA, take another language that can be solved by a DFA, and I want to show that it's closed under union. It's closed under concatenation and things. So here, what do we know? If it's a language that can be solved by a DFA, then what does that tell us? That tells us that there's a DFA that can solve the first language, and there's a DFA that can compute the second language, right? That's what it means for it to be in this set. Well, now what are we going to do? We want to say, hey, if that's true, can I come up with another DFA that solves the union of them, right? I'm going to take this machine as input, I'm going to take this machine as input, and I'm going to produce a new machine, right? And that new machine is going to compute the union of the two, right? And that will prove to me that the set of languages that can be computed by a DFA is closed under union. Are you following that? And how do we prove this? I'm going to give you an algorithm that has to go from here to here, right? In fact, this is exactly, those who are in 1090, this is exactly what we were doing in 1090 today. We're saying, if there's a problem that can be computed by a Java program, then there's a Java program that can do it. And then I can convert that Java program into a Turing machine that can do the same language, right? So this is what we're doing. You give me two languages that can be done by DFAs. If they can be done by DFAs, then there exist these DFAs that do them. And now what we're going to do is we're going to have an algorithm that takes as input two DFAs. Here's one DFA, here's another DFA. And what it returns is it returns a third DFA. And what happens is that the language of the third DFA is the union of the language of the first DFA and the language of the second DFA. All right, is that making sense? Everybody good? So here are various things that we want to get, see if it's closed under. All right. Is it closed under union? Is it closed under intersection, complement? Is it closed under concatenation? Is it closed under clinging star? And what we want to prove is that it's closed under all of them. And this proof will take, we're going to spend the entire week, this entire set of slides is dedicated to proving this. Okay? Some of them are obvious and some of them will be hard to prove. All right? So here now we can talk about regular expressions, right? Now the set of regular expressions, we want to know, is the set of regular expressions closed under union and concatenation and stuff? Well, here it's really obvious, right? If you give me some, here, if R reg 1 is a regular expression and R reg 2 is a regular expression, then here's a function that takes two regular expressions and outputs a third regular expression. What's the third regular expression going to be? It's the union of the first two, right? And this is a regular expression, right? And what does this regular expression represent? It represents the language, which is the union of the language represented by this regular expression and the language of the regular expression by this. So, and that's the same true for concatenation and for star, right? Now, what about intersection? Intersection isn't a regular language. It's a regular thing. It's an extended regular thing, right? So if we go to extended regular expressions, then they're closed under all of these things, right? Extended regular expressions are definitely closed under all of these operations, right? But regular expressions, as far as we know, they're closed under union and concatenation and clinging star, but we don't know whether or not they're closed under these other things. Are people following this?
Is it because like for the regular expressions we can't write it with the intersection and complement?
Exactly. Exactly. By the definition of regular expression, we know if we have a regular expression for one language in another, we can do the union of them. That's the definition of regular expression, right? But they don't have intersection and intersection and complement. So we don't. It's not clear that they're closed under right. It could be that there are things that you can. It could be that there are L1s that you can do with a regular expression, and there are L2s that you can do with a regular expression, but you can't do the intersection with a regular expression, right? It's possible that that's true, but it turns out not to be true. But the proof will be very hard. All right. So now let's prove these things. These ones are easy to prove. We're going to show that given a DFA that solves one language and a DFA that solves another language, we're going to come up with a DFA that solves their union. And then we're going to come up with one their complement. And then we're going to come up with one that solves their, then we're going to try to come up with one that solves their concatenation and their clinging star, but that will fail.
Sorry, Jeff, can you repeat that?
Then we'll get stuck again. Yeah.
Sorry, could you repeat that?
All right. So what we're going to do right now is that's what I'm trying to do. What I said was what we're going to do next. What we're going to do next is if you give me a DFA for one language, you give me a DFA for another language, I can come up with a DFA that computes those languages unions, those languages intersection, the complement of those languages. I can do each of those things.
Okay.
Right? So that won't be hard. Coming up one that does the concatenation and the star, that will be hard. Right? So that's why I don't have them in here yet. We will do them, but it'll be hard.
Okay.
All right? So right now we're just catching the low-hanging fruit. We're doing the ones that are easy. All right? So here is what we're doing. You give me two machines, and I want a machine that does the intersection. So let's first come up with an example, right? Remember this example, all strings that have at most, right? So here's a language, here's a machine that calculates, does alpha have at length at most 3, right? It just counts the length and sees if it's a length 3, right? Here's another language that's looking, does the string have an odd number of ones, right? So here's a piece of code that figures out whether the number of ones is even or odd, right? And what we want is a language that does the intersection, right? We want to say yes if it has at most 3 ones, 3 characters, and the number of ones is odd, right? How do we do the and of these two? Well, you can imagine how to do it. You have to run both this program and you run this program in parallel, right? And then you say yes if both of them say yes, right? So we have to run them in parallel. And how do we run them in parallel? Well, this one is running, keeping track of length. This one runs and keeps track of what the number of ones is even or odd. So this program is running and keeping track of both of them, right? And then at the end, it knows both the answer to this and the answer to this, so it can answer the and. Does that make sense? So let's go over to DFAs, right? Remember up here, right, what do we have up here? It's a DFA that computes is the length longer than 3 or not. How do we do it? Well, it's of length 0, then we start here, it's of length 0. We get a character, it's of length 1, it's of length 2, it's of length 3, it's a length more than 3, and then we stay in that it's of length more than 3, right? So what is this machine doing? It's remembering the parity of the number of ones. We start off with 0 ones, which is even. And then if we get a 1, we go to odd. We get another 1, we go to even. We get another 1, we go to get odd. We get a 0, we don't change the count. Right? Does everybody understand this machine and this machine? All right, so now what's the union machine? Right? Here we did sort of a cross product of this machine and this machine, right? This machine in the middle is running this and this, right? So, I'll have this, here's a matrix, right? For every state here, I have a row, right? And for every state here, I have a column, right? And so any state here, if I'm in a particular state of this machine, then I know both what state this guy's in and what state that guy's in, right? Here I'm saying for every ij, I have a state ij, which tells me my first machine is in state I, and it tells me my second machine is in state j. Does that make sense? And then we have to come up with the transition functions. So how do we do that? This is just counting for a minute how many states we have, right? This has C state, so it's kind of remembering log C bits of information. This guy has C2 states, so it's remembering log 2 bits of information. So how many states does this have? It has C1, oops, that's a typo, C1 times C2 states, right? So it has C1 times C2 states. Right? And so the log of that is the log of C1 times C2 is the log of C1 times the log of C2. And that's just kind of say, well, my algorithm has to remember both of these, has to have bits to store this and bits to store this. So it has to have the bits to store both of them. Right? Does that make sense? The algorithms run in parallel, so they're required to keep the information of both. All right, so now I like little gnomes. All right, so here we got 3 gnomes. The one gnome is running the one program. The other gnome is running the top program. And what is the gnome in the middle? He's running the middle program, right? And they're all start states, right? Well, what we're going to maintain is that where is this middle gnome? He's wherever, he's on the row that this guy is on, and he's on the column that this guy's on, right? So he's sitting there, and what comes is we get some character, right? So the next character is a 0. Well, oops, here the next character is a 0. So where he's going to go over there. Where's he going to go? He's going to stay there. So where does this guy go? He follows them, right? This guy stays put, and this guy moves, right? Now we get a 1. We get a 1. What's this guy going to do? He's going to come down here. what's this guy going to do? He's going to move across. So they all do their thing, right? This gnome is following both what that guy does and what this guy does, right? So now the next character is a 0. So the first gnome stays put. The top gnome moves along. So what does the inner gnome do? He moves along in the same row, right? And then what are we reading next? We're reading, I've lost track. Are we up to a 1 again? So he moves, changes places, he moves forward, and our gnome, right? A gnome follows both of them, right? Does that make sense? Right? And here I'm writing it down. Say if the first program, if df1 when in state qi and reading as c goes to state qi prime, and dfa2 goes from qj reading as c to qj prime, then our new dfa when in state ij reading the c is going to go to state qi prime j prime. Right? Does that make sense? All right. Any questions about that?
But then the first one, the one with the length.
Yep.
More than 3 length, right? So how would
Yep.
that work out? We're just gonna like keep looping on the last circle?
Yeah, because remember, we can't count forever because we can't have an infinite number of states. When we build the machine, it has to have a fixed number of states. And so this machine will count length up until it's greater than 3, and then it stops counting.
Okay, and then it's gonna output the false, right? Because it is bigger than 3?
Yeah, exactly. Exactly. I haven't said true false yet, right? You notice here I purposely got rid of the true false. So let's bring true false in, right? This guy here at the length, we want to accept if the length is shorter, is 3 or less. Here we want to accept if the number of ones is odd, right? So where do we accept here? Well, if we're doing intersection, then we accept when this is true and when this is true. So we accept, those are our accept states, right? All states for which this and this are true. Does that make sense?
Yes.
Right?
Sorry. So we're doing intersection? I thought we were doing union.
We're doing all of them. We're doing one at a time. Right now, we're doing intersection. Why are we doing intersection now? Is because that's the example we did in class a while back. It was an and here, right? So if this is true and this is true, then it's a union. Then it's an intersection, right? And there, those will be our accept states, right? So if you wanted to do union, yeah, let's skip all this. This is sometimes I put here's more formal proof that it works, and we're just gonna skip over that. All right. So now how do we do union? Right? Well, now we're going to accept if it has at length the most 3 or the number of ones is odd. So now we're going to accept if it's in the one language or it's in the other language. So if we're accept if one of these is, if this is true or this is true. So which ones is that? Here, look at all of these guys here has this is true or this is true, right? In fact, the only one we don't accept, right? Remember De Morgan's law. If we accept when this is true or this is true, when do we reject? We reject when this is false and this is false, right? That's when we reject by De Morgan's law. Everybody get here how we're doing the intersection?
Isn't this union?
Oh, union. Right, this is union.
Okay. Sorry, could you explain the De Morgan's part again?
Well, you happen to be in 1090, I know, so you need to know De Morgan's law, right? A and B right? Oh, here, this is A or B, right? A or B. Well, if A or B is not true, it means that A is not true or B is not true, right? So when do we accept? When we accept when A is true or B is true, right? Here A is true, here's A is true, right? Here's A, I don't know which one's A. Maybe this is A. So all of these A's, oh, here, A is true, right? So here A is true, so we accept all of those guys. I don't know why that one fell down. Here, B is true, so we accept those, we accept those, we accept those, we accept those. Who do we not accept? We don't accept if A is false and B is false,
Okay.
right?
Okay.
Can I
Now,
ask
what-
a question though? I'm confused about why the last row, like, I'm confused why even and length greater than 3 is false, but odd and length greater than 3 isn't.
Here?
Yeah.
Well, this is true because that one's true. Right? Here it has an odd, if you're here, it has an odd length, right? It has an odd number of ones. I don't care, right? Because there's an or. Suppose I have a string that's really, 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 really long, but it has an odd number of ones. Then we're going to accept.
But wouldn't that also be true if it was really, really long and had an even number of ones?
No, because if it's really, really long, then this is false and this is false.
I think it's because if it's even, it's false, and if it's what do you call it, the length is greater than 3, it's false. So both are false. So like the new DFA is gonna be like that one's gonna be false.
Oh, I understand. Okay, thanks, Addie.
No problem.
See, sometimes it's hard to, I thought I'd move that little guy, but he doesn't want to move. All right, everybody, right? All right, so now let's do complement. This language is accepting when you have an odd number of ones. Oh, here, this is L1, I guess. If this, what's the complement of L1 is you want things that have longer length, right? L complement accepts longer length. And L2, well, accepts odd number, right? So now what happens if I want to do, it has L1's not true and L2 is true. That, right? That's an and, so that's this guy. This guy is when L1's true and when when L1 is false and L2 is true. We get that one, right? Everybody kind of follow that?
Wait, sorry, could you repeat that again?
Here, suppose I want to compute the language that is the complement of L1 and L2, right? Well, what was L1? L1 was that it has it's short. What's the complement of L1? It's long.
Oh, I didn't know the top one was L1. I thought that was L2. Okay.
Yeah, I get yeah. Let's have that one be L1. I should label it up there, which is which, right? And then, and so we're there, right? Does that make sense?
Yeah, I get that.
So so the bottom right is the accepting state in the cross product. Is that what we know from this?
This is the accepting state when, if we only want, here, what do we want? We want strings that, and, because it's intersection, and L2 says an odd number of ones,
Okay.
right? That's that state.
Oh, okay. So that would be the accepting state, and that satisfies the intersection that
This-
we have.
This
Oh,
guy
okay.
here, right?
Okay.
And you can imagine doing all combinations of them, right?
Okay.
All right, so now that showed that DFAs are closed under union, intersection, and complement. Everybody understand that?
Yeah.
All right. So now let's try to do concatenation in clinging star. And why did I make it red instead of green? Is because we're going to fail. All right, we're going to try something that's obvious, and then we're going to see that the obvious thing does not work. Now, is DFAs closed under these? Yes, it is. But the obvious method to prove it does not work. All right? So let's remind ourselves what concatenation means, right? If you take two languages and you concatenate them together, it means you can take any string alpha from the first language and any string beta from the second language, and you can concatenate them together, and that will be in our new language, right? So now you'll note here I said there's an N here, but we're talking about DFAs. So let's, for a minute, pretend that N wasn't an N, but let's pretend it was a DFA. All right, so let's have this be a generic DFA, right? It has a start state, it has a bunch of states, and then it has an accept state, right? Here's another generic DFA, right? It has a start, a bunch of states, and then it has, this one happens to have two accept states, right? And somehow we want to compute L1 followed by L2, right? So somehow we want to join them together, right? We want to first we want to read in alpha and see it's in L1, and then we want to read in beta and see if it's in L2, all right? So what's the obvious thing to do? Well, we read in alpha, there, we read in alpha. We read in beta, okay, that accepts beta. So what do we want to do down here? We want to read in alpha, and then we want to somehow get over to this start state, and then we want to read beta, right? People following that? Now, that looks good, but here's the problem, right? What happens? A couple problems happen. What happens if there's a little loop here where when we read a character, we could stay in this state, right? I mean, we may go back to the state many times, right? And so, for example, oh, here, I guess this edge here is labeled A. Well, when you read an A here, do you keep reading the same language, or do you go over and start reading the second language, right? You don't know when to stop one language and read the second language, right? And so who's going to tell you how to do it is we need an NFA. We need a fairy godmother, right? It suddenly becomes an NFA, right? Because if I have, right, if there's a loop here, A, and I read an A, well, maybe I want to start reading this A, or maybe I keep reading A's in alpha. So that's not working. So here's just an example, all right? So suppose we want to have the language omega contains 0101. Remember, we did this example a few times in class, right? And so here's a regular expression that does it. Any characters followed by a 0101 followed by any characters, right? And so now we got this language concatenated with this language concatenated with this language. So let's build an NFA that does it, a DFA, right? That's computing any string. This is computing 0101. This one's computing, oh, look at this, isn't quite long enough. That's funny. It's supposed to be 0101. This is only 010. There's so many bugs I'm finding in the slides. All right, so you put them together, right? And you get this machine, right? But is this machine a DFA? No, this machine is an NFA, right? Because here you read a 0 or you go forward 0, right? So if you do this obvious sort of building, then it's great, but you're building an NFA, right? And how does this read? It can, when you get a 0, you have a choice. Do I go forward or do I go around, right? You have a choice. But which one do you go? I'm claiming it's an NFA, so you have to have the fairy godmother tell you which way to go, right? There exists a path. Now the DFA, what's a DFA for this language? It's much more complex, right? Does that make sense? So do we know that these work? Well, it's not obvious how they get them to work, but let's go and work on closing NFAs on these various things, right? I'm going to show you how to close an NFA on union and on concatenation and star, but these ones are going to be hard. All right, so let's do concatenation. We kind of did it already. Right, so if you have an NFA for this and an NFA for this, all you do is you take those two NFAs and you put an epsilon transition. Remember, epsilon transitions where you can follow that and you don't read any character, right? And you have it go from every start state of the first machine to from every accepting state of your first machine to the start state of your second machine, right? And now I claim that this machine accepts the concatenation of this machine and this machine, right? Why is that? Well, because of alphas in the language, right? Right? We say, right, when does a machine accept down here? It accepts, alpha accepts a string, the machine accepts an alpha if there's a path labeled in the NFA ending in an accept state, right? So because it's in the language, there exists some path that goes there. Well, similarly, there exists some path that does beta. So we combine them and we get a path that goes here, right? Does that make sense? But we need to do an if and only if, right? And this is a little harder. If there's a path here, right? Suppose you have a path here. Well, if you have a path here, then it has to cross one of these epsilon edges at some point. At some point, you have to commit, right? So take any path from this start state to an accept state. At some point, it has to cross this barrier. And how does it cross this barrier? It goes across an epsilon thing. And that's a commitment, because once it does that, it can never go back. And so the path beforehand is all over here and is accepting alpha. And the path over here is all over here and it's accepting beta. And so if a string is accepted by this machine, then there's some place to cut it such that the first half is in L1 and the second half is in L2, right?
Sorry, I don't really get the whole commitment thing. Like, how do you know like when to commit or why you have to commit? Like, I don't understand.
Well, can you imagine that if you're trying to travel from the start state to an accept state here, how can you get, we have these two circles. How do you get from one to the other? You have to go across this epsilon edge somewhere, right? It's the only way to get from here to here. There are a lot of edges in here, and there are a lot of edges in here. But the only edges moving from one to the other is going across one of these epsilon transitions, right? That's why you have to do it. And why do I say it's a commitment? Well, it's a commitment because once you do it, you can never come back, right? You can compute about L1. You can read alpha in L1 as long as you want. But in order to move over to L2, you have to get to an accept state of L1, and you have to commit by going over one of these epsilon transitions. And when you do that, you're going to now be over here and you're going to be reading beta. You can never go back and read more characters over in the L1 side, right? So that tells us that the characters on this side are going to all be alpha together, and the characters on this side is all going to be beta together.
Okay, but like, so the accept states for the first NFA, why isn't like the final NFA, why isn't it like an accept state in the final one?
Because we need for it to be a concatenation, we need an alpha and a beta. So our machine down here is only going to accept when we've read in an alpha and we've read in a beta.
Oh, okay. Thank you.
That makes sense?
Yeah, thank you.
All right, so now let's do the star thing, clingy star, right? Given a language L, what's L star? Well, you can choose any R, integer R, which is greater or equals to 0. Then you choose independently, choose R strings alpha that each are in L, and you concatenate them together, right? That's our clingy star. So what are we going to do? We have an NFA that does the one machine, that does L. And how do you build an NFA that does the star? All right. Well, first, you have a brand new start state. That's also an accept state. And that's going to accept the empty string. And we'll see later why you need that. But right now, just trust me, you need this extra start state. And where that start state going to go, it's going to have an epsilon transition to the start state of this machine. And over here, what we got is a copy of this machine. We take this machine and we copy it over there. How do we build this NFA? You take this machine, this NFA, you copy it over here, you get a new start state. You have that start state's an accept state. You have an epsilon transition to the start state of the other NFA, right? And then you take from every accept state of this NFA over here, you draw an epsilon transition to its start state, right? Everybody see how we're taking this NFA and we're making this NFA?
Not really.
All right. So
Sir,
this
I have
is,
a question.
yeah.
Why are we making the transition from why are we putting the epsilon from the
All right. So
specific state to
you're asking questions about the future. So let's hold off until I do the slides about that.
Okay.
Right now, we're just trying to get what we are doing. All right. Just the mechanical algorithm. I give you an arbitrary NFA. What it has a bunch of states, it has a bunch of edges, it has a start state, it has some accept states. I take a machine here, and I want to build a new machine. How do I build a new machine? Take the previous machine and copy it over here. And then, in fact, you can do this on a test. I give you this machine. What do? Well, actually, on the test paper, what I like to do is not copy it at all. I draw it right on the test question, right? So if this is the exact test question, then what I do is I make a new start state. That's an accept state, and I draw an epsilon transition to the old start state. And then for every accept state, I draw an epsilon transition to the previous start state. That's what I do. Everybody understand what we're doing? Building this machine, from this machine, we build this machine.
Yep.
Okay, now let's try to prove that it works. All right? We have to prove that if this machine, right, if something's in the language, then this machine is going to accept it. All right? So suppose we have a string that starts with alpha 1. Then there'll be a path, alpha 1. And then, so what we're going to do? Well, we're going to commit to starting. Here we commit to starting, and then we're going to read alpha 1. That's what, right? If this machine accepts alpha 1, then this machine is going to get here for alpha 1, right? So now we know that alpha 1 that's an accept state. So alpha 1 is in L star. And sure enough, if alpha 1 is in L, then alpha 1's in L star. All right? But we might want more stuff, right? So we're going to come back up to the big start state again. And then we're going to, let's say now there's an alpha 2. Well, if alpha 2 is in the language, then there's a path here following alpha 2. So we're going to follow that alpha 2. And then so now we know that alpha 1, alpha 2 is in our L star. Well, maybe we want to keep going. So we take epsilon transition up here and say, oh, now there's an alpha 3. So we read an alpha 3, right? Everybody follow that? So what we're proving is if this string, alpha 1, alpha 2, alpha 3, up to alpha r, is in the L star, then that means each of our pieces, L1, L2, each alpha I is in L. And if each alpha is in L, then each alpha follows one of these paths. And then we can combine them to get a path in this machine. Right? Everybody buy that? It says if it's in the language, then this machine accepts it. Then we want to go the other direction. Right? Suppose we have some big crazy string that's accepted by this machine. Right? And I want to prove to you that if it's accepted by this machine, then it's an L star. All right? How do I prove it? Well, I start by running the machine. I know if it's accepted by this machine, there's some big crazy path. Some big crazy path that goes from the start state all the way to an accept state. Right? That's the definition of this machine accepting the string. Right? And so I'm going to take this path and I'm going to break it up, the path up into pieces, right? Every time it does one of these back epsilon transitions, I'm going to cut the path into pieces, right? Because that's what, when you do this epsilon transition, I call that you're committing to something. You're committing to ending one alpha and starting the next alpha. So I take this path and I cut it up. There I cut it up based on when you do those transitions. And now, correspondingly, each of those paths, I cut up the string based on what it's read by each of those subpaths, right? And now I look at each of those subpaths. What is the subpath doing? Well, it's doing from here to an accept. Well, so that means alpha 1's in their language. What about our second subpath, right? Remember, between this path and the next path, we took some epsilon transition because that's how we cut it up. So our next path is going from the start state to an accept state, right? So it's accepted by the language. And alpha 3 is accepted by the language. So that means the whole string is in L star, right? So we proved two things. If the string is in L star, then this machine accepts it. And if this machine accepts it, then this whole string is in L star. Right? Does that make sense? Right? The epsilon edges make the path commit. When you take that epsilon path, you're committing to starting a new alpha. All right, now people might ask, why did I have a separate start state? And the reason is because maybe the empty string is not in our language, right? If our empty string's in the language, it's not fine. But if empty string's not in L1, in L, then its start state, if it is not an accept state, right? But L star always contains the empty string. Why? Because you can have R be 0 and you take nothing from L, right? So the empty string is always an L star. So we always want to start accepting the empty string. But then when you want to start reading characters, you have to commit to saying, I'm not the empty string. And then you start accepting again, right? But you never want to come back to this state. Once you say, I don't have the empty string anymore, you never can go back to this state. and that's why we have to do that. And I think I have an example here, right? So here's an example. What's this language? Right? It accepts A, right? Anytime it ends with an A, right? It has to go A, B, star, right? A, B, star. You can do A, B as many times as you want, but you have to end with a B, right? Everybody buy that that's what this does? A, B, A, B, A, B, A. That's what it reads. It accepts, right? Now, if we build an NFA without this extra guy, we just put an epsilon back, right? Now, it should still end in an A, but it doesn't end in an A, right? We could go, I don't know, what does it do? Somehow this is wrong. If we made that an accept state, right? Right now, it doesn't accept the empty string, right? This is no good because it doesn't accept the empty string. But if we put that in, then it accepts everybody, right? So that's no good. So instead, we want to, how do we build this machine? We have a new start state. And then from every accept state, we go back to the start state, right? Everybody see if this is L, then this is L star. That's not L star because it doesn't accept empty string. This is not L star because it accepts everybody. That's L star. Everybody good? So now, so everybody got, we did NFAs are closed under intersection, and they're closed under star, but now we're going to close under union, right? All right, so now we're going to do union, right? So what's the union? Alpha's in language or alpha's in the other language, right? So here's a machine that does the first language. Here's a machine that does the second language. And what do we want? Here's going to be a machine that's going to do the union. And how do you do it? You take this first language and machine and you copy it over there. You take the second machine and you copy it over there. And then you have a new start state that's not an accept. And you epsilon to the start state of that and the epsilon to the start state of that. Right? That's how you do it. And let's prove that it works. Well, if alpha is in the union, then it's in one or the other. And if it's in L1, then there's a path. And so then there's a path over there. Right? And if it's in the other language, then it's accepted by the one, so it's accepted by the machine. Right? But now let's go the other direction. Suppose there is a path that goes from here to here. Well, then it has to commit to going one to the other, right? Any path from the start state to an accept state, it can't travel between these. It either has to commit to doing down here or it commits to doing down here. And if it commits to coming down here, then we know that it's an L1. Otherwise, it's an L2. Right? Does that make sense? Everybody getting union? All right. Now what about intersection? So we want to, if this is the machine for L1 and this is the machine for L2, how do we say that it accepts both of them? How do you say it's an L1 and it's an L2, right? I don't know how to do that, right? How do we follow a path in both of them? And that's hard. Everybody following that? So how do we do the intersection? Well, we showed how to do the intersection already, right? you have to do it this way. You have to run both of them in parallel. And so this method, if this is an NFA and this is an NFA, then this method also works for NFAs, and we can do intersections, right? And this method also works for, oh, here, let's try complement. Oh, have we done DFA complements? I don't know if, I don't remember doing DFA complements, but we should have. Suppose that this was a DFA, and what we did is we just changed all the accept states to the non-accept states and vice versa. We just flipped which are accept and which is non-accept, right? So I claim that if this is a DFA that accepts L, then this is a DFA L that accepts the complement. Right? Why? Is because if there's a path that accepts here, then over here, right, a DFA only has one path. So given a string, if it accepts, there's one path that goes to the accept, and that one path here will go to the reject. Versus if the string is not in the language, then there's one path that goes to the reject. And here the one string will then go to an accept. Right? But for NFAs, there could be more than one path. Right? So alpha could follow this path and this path. And in which case, here, this machine accepts it because it's going here, it's going to an accept state. Right? Well, over in this machine, that has the two paths, and this one will also accept because it's going to an accept state, right? So that doesn't work. And so how do we do complements? Yeah, it's not clear how to do complements, right? This method of complementing their states doesn't work. Right? Any questions about this? So everybody kind of buy, we filled in this whole table here, right? All except for the red question marks.
Mm-hmm.
All right. Now, what we're going to do is we're going to work on a slightly different topic. We're going to come back and fill in these question marks. Well, one thing that's kind of interesting is that every row has at least one yes in it, right? Right, for you, right? So now we just have to, that's how we're going to fill in the others, is we're going to translate between them. So now we're going to do another thing. This is kind of what we're talking about in 1090 now, is talking about translating from one of these models to another. We're going to prove, right, if a DFA can do it, then an NFA can do it. And if an NFA can do it, a DFA can do it. If an extended regular expression can do it, a regular expression can do it, right? So what is a complexity class? It's a set of computational problems that have a similar difficulty, all right? So these problems are all computable. Everybody in this set are computable. Everybody in this set can be solved by an exponential time. Everybody in this set, every problem can be solved in polytime. Every set in this can be solved in linear time, right? So here is the set of problems that can be solved by DFAs, right? Now, if you can solve it by a DFA, how much time does it take? DFAs just read each character one at a time. So if it can be done by a DFA, it can be done in linear time. So this just says if you can do it by a DFA, then you can do it in linear time. If you can do it in linear time, you can do it in polytime. If you can do it in polytime, you can do it in exponential time, right? So let's blow this picture up, right? We switch to, oops, right? Now here's linear time versus DFA time, right? So these are the guys that can be solved by a DFA. Well, what about the problems that we can solve by an NFA? See, it's a slightly different blue, right? Well, let's think about it. If a DFA can do it, can an NFA do it? Yeah, because an NFA, a DFA is an NFA, right? Just like a puppy is a dog. So, first off, if an NFA can do it, then you can do it in linear time, right? And and it's not clear how to do it. Yeah, you have to do depth first search to find a path, right? So you're looking for all paths. So you do depth first search through your NFA to do all paths. And you might not know this, but you can solve depth first search in linear time. All right. So if these are the guys that have been done by an NFA, so there's a machine that can do it in linear time, and each DFA is also an NFA. So that's why we have this picture here, right? What are we saying? We're saying if an NFA can do it, then we can do depth first search and we can do it in linear time. And we're saying if a DFA can do it, well, a DFA is an example of an NFA. So if a DFA can do it, then an NFA can do it. Right? People understand what this picture means? If a DFA can do it, well, a DFA is an example of an NFA, so an NFA can do it. And if an NFA can do it, then you can do depth first search and you can solve it in linear time. All right? So now we're going to do something else. You're going to give me an NFA, right? You give me an NFA, and I'm going to convert it. I'm going to have a program here called NFA to DFA. You give me an NFA, I'm going to give you a DFA that does the exact same language. All right? And what's that going to prove to me? That proves to me, here's a language, right? If it has an NFA that can do it, then there's some NFA that can do it. So I can translate it into a DFA then do it. And so a DFA can do it. So it says if an NFA can do it, then it comes down a DFA can do it. And what does that prove to us? That proves that these are the same classes. It says anything a DFA can do, an NFA can do, anything an NFA can do, a DFA can do. So they're the same class. Does that make sense? What about regular languages, right? If it can be done by a regular language, then clearly it can be done by an extended regular language because regular languages are examples of extended regular languages, right? So here you can do there, right? How long does this take? Well, one thing that we're gonna come up with an algorithm, which if you give me an extended regular expression, right? You give me an extended regular expression, I can build the DFA for it, right? So it's going to be a complicated proof. I mind you, it's a complicated proof, but you give me an extended regular, I'm going to give you a regular. So what does that tell me? That tells me if an extended regular can do it, then a DFA can do it, right? And what does that do? That puts this whole guy inside, right? Because if a regular can do it, then an extended regular can do it. And if an extended regular can do it, oh, then a DFA and an NFA can do it, right? That's what we're going to prove. Well, the next thing we're going to prove is, That's what we were doing here. You give me a regular expression, I give you a DFA. Oh, actually, that's not a hard proof. That's a pretty easy proof. All right. The hard proof, this one's a hard proof. You give me an NFA, I give you a regular expression, right? That says if an NFA can do it, then a regular expression can do it. Not even an extended regular expression. A regular expression can do it. So we're going to convert from you give me an NFA and I'm going to give you a regular expression. And that proves that everything there is there. And that's going to collapse all these sets into one, right? So if you give me any of these, you give me an NFA or a DFA or an extended regular expression or a regular expression, you give me any of those, and I can convert them into any of those, right? And what are we going to call these expressions, these languages? We call them the set of regular languages. All right. Now, this guy here is not so impressed. He says, well, it doesn't surprise me that NFA, that non-determinism doesn't help a DFA. Why? Because why isn't he surprised? Doesn't help me. Oh, he says it does help. Oh, sorry, that's why. He says it does surprise him that non-determinism doesn't help, right? And it surprises him that union and complements don't make regular expressions stronger, right? That, in some ways, that's surprising, right? But the reason it's not surprising is because when you do it, everything blows up. There's an exponential blow up in size. If you give me an NFA, I can give you a DFA. But if the NFA has R states, then the DFA will have 2 to the R states, right? If you give me an extended regular expression, it may have R characters, but the regular expression may have 2 to the R characters, right? It's always a fixed number of, right? Because the DFA has a fixed number of states. The NFA has some fixed number of states. The DFA has a fixed number of states, but it has a lot more states. Does that make sense? So that's what I say. If an NFA has C states, then a DFA has 2 to the C states. I don't know why I'm saying time there. All right, so here. So now what about our closure properties, right? Well, because there's a yes in every column, that automatically fills in those guys there, right? Because we know that these guys are closed, and then we know extended regular is the same. So that gives us all of these. All right. And the way we get the closure is we go through these other models. All right. So this is just the warning of what's coming. Here's the language A star, B star, right? Is it a regular expression? Well, certainly. It's right. It's the number of A's followed by a number of B's, right? The first is easy, but the second, here what this is some number of zeros followed by some number of ones, and they have to be the same number. So to accept this, you have to count the zeros, and an NFA and a DFA can't count. So those guys, you can do it in linear time, right? You can solve this problem in linear time. You count the number of zeros, you count the number of ones, you see if they're the same. But if they're not, but it can't be done by a deterministic finite automata because it doesn't have enough memory to count. Does that make sense?